All right, so hopefully this all works out okay. So for people watching this in the future, I'm just going to read off the chat box because you won't be able to see the chat box because I'm recording on Vidal. Someone's currently on a car trip to Utah. They weren't able to print the notes. The printer decided not to work at the worst time. Oh man, well, it's okay. You can just write the stuff in your notes on a paper and then just copy it later. It'll all work out. It's just a little easier if you have the notes in front of you. You just do your best with what you have, right? So we're going to actually start talking about calculus today. Jumping right in to Unit 1.1. So this week we are talking about Unit 1.1, 1.2, and 1.3. I posted the homework, so quick notes about the homework. Let's see. At the end of every section, let's see if I can find it. If I can find it in here. Is it this? No. At the end of every section, there are problems in the back. For sections 1.1, 1.2, and 1.3, I suggest you do all the problems that are in these guided notes. There are answers to all these problems at the, what is going on with this one? Oh, there we go. At the very end of the entire, so like page 43 of the PDF, there are answers to everything. Not full done solutions, but answers to everything. So I suggest that you do all the problems from, come on, computer, from Unit 1.1, 1.2, 1.3. However, I will only be collecting a few of those problems. I don't have those ones written down, but they are posted on Canvas. So there's only 3 problems I'm asking you to actually write down the work for, and I do want you to write down all the work for those problems. So write out the nitty-gritty details. There's only 3 of them you have to do to turn in. Write out every step. You have the answer, right? I've given the answer to you. I'm not interested in you getting the correct answer because the correct answer is already there. I'm interested in the work that you did to get there and how you present your work. So make sure your work is neat, make sure it's mathematically sound, make sure you're showing all the steps, so on and so forth. If you have questions about whether or not what you've provided is good enough, submit it, send me an email, and I will let you know how it looks. I am still in the middle of getting through all of the introductions and practice. I think all the practice uploads I might have graded, but I'm still getting through all the introductions. I'm sorry I don't have them all graded yet. I'm enjoying reading through everybody's though. Okay, let's get started. So actually talking about calculus, we're going to talk about the definition of a limit. Now, this section is going to look a lot more mathy than it needs to. It's one of my complaints about calculus is that it kind of starts off in this really, really mathy zone when it's really not as mathy of an idea as it appears. We're going to be talking about limits, and there's a really scary picture here. I'm just going to kind of scroll to the side really quick. If you have scrap paper, this would be a good time to bring out some scrap paper. All right, I'm going to draw a function. I don't know, it looks like this. It doesn't matter what it looks like. All right, and if I plot a point here, and this is the x value, over here is the value f of x, right? The y value is what we call f of x. If I know where the point is, I can tell you what this value is, right? So like if I was told that this was 2 right here, I could say that f of x is equal to 2. This means that the y value is 2. However, with the game that limits play, what color do I want to use? When we talk about limits, it's as if all of this disappears. All right, all of this disappears. And now we don't know exactly where what this graph looks like right where the x is. We don't know what's happening right here, but we have to guess. So limits are all about guessing what the y value is at a given value when we don't really know what that value is. We don't know exactly what's happening around it, but we have a good gist, right? We have this like picture that's like, okay, well, it's very unlikely that the graph does, something crazy in here. It's very unlikely that it does like something like that, right? We have a pretty good idea that it probably does something like this, but we're not certain. So all limits are doing is trying to guess what the y value is at a given x value on a function. So let me come back over here and there we go. So here's the math definition. Let I be some interval containing x equals a. In this case, here's an interval. You could call this a, right? It contains x equals a. And let f be some function defined on that interval, except possibly at x equals a. That is, f of a may or may not exist. So what that's saying is that we don't really know what's going on in this function in this area. It is very possible that it looks like this. If it looked like this, then it wouldn't actually be defined at f equals a. So this little open hole here, that would mean that it's undefined at that point. So if this were the case, then f of a does not exist because there's an open hole there. There's no y value because it's an open spot. But what we care about with the limits is what it looks like is happening, where it looks like there should be a point. The notation that we use for this, and you can do it however you want. When I first learned calculus, I learned to do this in cursive. So we would always write the limit in cursive, but you can also write LIM. And then underneath that, as x approaches a, so it's x and then an arrow a, of f of x equals L. This is the notation for limits. This is saying that it looks like as x approaches a, so as you get closer to the x value a, it looks like the y value of the function will be L. So back on this picture, if this were an L, some y value, then we could say, oops, if I could write the word limit, the limit as x approaches a of f of x is equal to L. It looks like as we get closer and closer to the x value a, that the y value will become L, right? The value of a limit is the y value. It's the y value that it looks like the function is approaching. And if you need me to scroll back or anything, I do have the chat box open so I can see what you guys are typing. I'm not going to talk about this delta epsilon definition. I'm not going to do it. So I'm not going to talk about this. I'm going to erase it. I know you don't have the courtesy of doing that, but I'm not going to talk about the delta epsilon definition. The delta epsilon definition is a lot more complicated than we need to get into. If you're interested in looking it up sometime, I can tell you that you can look up the, oops, that is too big, the delta epsilon definition of a limit if you're really into it. You can do that, but I'm not going to go into it. That's for those of you really into math. I will tell you, I didn't learn the delta epsilon definition of a limit until I was in my senior level math courses in my undergrad degree. So it's interesting that it gets put into these lower level courses. Right? And I'll make a note here. This is the y value, one more time, the y value that the function is approaching, that it appears the function is approaching. So once again, I'm not going to talk about this delta epsilon band thing. If you're really into it, you can go look that up. So sometimes instead of writing this, and very rarely, most of the time we are writing this. But sometimes instead of writing that, we could say that f of x approaches L. So this little arrow, we say the word approaches as x approaches A. Can I answer any questions thus far? So the idea of a limit we're going to be talking about, and I know there's probably a lot of questions because you don't exactly see where this is going, but the idea of a limit is simply talking about what it looks like the function is doing as we get closer to a certain x value, what it looks like the y value will be. It really isn't a more complicated idea than that, I promise. When we start talking about it algebraically, it looks different, but the idea is the same. All right. So my spoiler alert, my husband made these notes. So we're both Seahawks fans, and this is his example that he wanted to talk about the intuition of a limit. Now, I don't know why these timestamps move backwards. I think that this is supposed to be time left in the video. I was actually going to bring that up to him right before I started, but then I forgot. But I think this is time left in the video. Just note time is moving forward in this video. So you're watching a totally legal stream of the 2018 Seahawks football game. Because your internet connection is slow, your video keeps on buffering. So the intuition of a limit is like, all right, here's his whole definition down here. At 13:11, Russell Wilson hands the ball off to Chris Carson. That's what's happening here. You see this happening. Then our stream shows at 13:10 that Carson is starting to get blocked by the defense. Right? You see this happening, you see him move, you see this happening, and then your stream starts to buffer. Right? You don't have any idea what happens from 13:10 to 13:08. So there's this 1 second gap where you don't see the screen, or the screen is frozen right here. When you regain the stream, you see Carson across the first down marker. So if you're watching this, right, for those of you that don't watch football, guy moves. Something happens. Guy is now past this yellow line. There's my non-football description of what's happening here. Guy moves. Guy's moving. He's not past the yellow line, buffering past the yellow line. In this time right here, we can assume that he passed the yellow line, right? We can assume he passed that first down marker because he wasn't past it, and then when we saw him afterwards, he was. So sometime in this 13:09 time, he was roughly around where this yellow line is. That's the idea of a limit. It's just, you don't know exactly what happened right here, but by watching this, you have a pretty good idea of what it should be. And am I certain? No. Maybe he flew into the air and then leaped and grew wings and then jumped back down here. I mean, yes, that could have happened, but probably not. Probably what happened is he crossed it on his feet, and sometime in here it would have looked like this, but with this little guy over here. That's what limits are in football, in football terms. So what we're going to do is figure out what this looks like numerically, so without using a actual graph. If you have a calculator, I suggest grabbing your calculator at this time. This is a good time to play with your calculator. I'm trying to decide what I want to do here, because I kind of want to show you how to do some stuff on your calculator. So maybe what I'll do, all right, sorry people watching this in the future, I just realized that you didn't catch any of what I was doing on my calculator. A quick recap though, for those of you who are watching live, you can type in the number that you want to store, and this is on the Casio FX991EX. You type in the number you want to store, you click on the STO button, and then you click on the X button, and that will store it in the X variable, and then all you have to do is push the X button whenever you want to put an X in. So after you've stored this in, oh, sorry, did somebody say something? Oh, sorry, I was just looking, I was just using this guy right here. If you have the notes in front of you, you can see the 1.5. I was just picking a number to show you.
Okay, thank you.
Yeah, no problem. So I was showing what this one would be, so I'm gonna actually go through this problem, but I'm trying to show you just the steps on how to store a number in your calculator so that you can easily do math. So then you would just need to push the X variable whenever you want to plug it in. So you could type in x cubed minus 2x squared plus 4x minus 5. And then it would act as if you plugged it in. So it would act as if you did 1.5 cubed minus 2 times 1.5 squared plus 4 times 1.5 minus 5 on your calculator. So anyway, coming down here. So at this point, we're going to figure out what f of x tends towards as we get towards 2. So if you're looking at trying to find the limit as x approaches 2 of this function, right? This is saying what's happening as x approaches 2 in this function. Now, we're going to find out very soon with polynomials, because polynomials don't have any problem areas. They don't break up. They don't have undefined spots. It really is going to be as simple as if you plugged 2 into this, that's what it's going to go towards. But we're going to play the game of plugging in numbers close to 2 in both directions, right? Because if we think of a number line, here's 2, you have 1.5, 1.9, numbers close to 2 that way. And then you also have these numbers that are slightly bigger than 2. So you have 2.5, you have 2.1. So if you try numbers that are bigger than 2, but getting closer to 2, and numbers that are smaller than 2, but getting closer to 2, if you go from both directions, you can figure out what that function is tending towards. So if I take 1.5 and I plug it into this function, I'm going to get negative 0.125, right? And this literally is the same thing as plugging this guy right up here into your calculator. For 1.9, that's as if you plugged in 1.9 cubed minus 2 times 1.9 squared plus 4 times 1.9 minus 5. So plugging in these x values to this function. So I did that on my calculator, and I've got 2.239. I'm going to do the same thing with 1.99 on my calculator. And the number I get is 2.920399. All right, so as I'm getting closer to 2, what I'm noticing, right, this doesn't tell us very much, but we went to 1.9, now it's 2.2, 1.99, now it's 2.9. Now I'm going to plug in 1.999 on my calculator, and I get 2.992003999. And then, we could put in more 9s if we wanted to, but it looks like as we're getting closer to our x value being 2, it looks like the y value we're getting out is 3, right? It looks like if we plugged in closer and closer numbers that we would get 3. In this case, if we look at the number line, we started here and we're going towards 2 this way. So we are approaching 2 from the left. Right? We are approaching 2 from the left because we are coming from the left side of 2. On the other side of 2, so if we start with 2.5 and we plug in 2.5 and we go this direction, which is approaching from the right. So we'll start with 2.5. And we get 8.125. We try 2.1. And we get 3.841. 2.01. We get 3.080401. We plug in 2.001. And you get 3.008004001. And if you keep on plugging in numbers that are closer and closer to 2, once again going in this direction, it looks like we're getting closer and closer to 3. So in either case, regardless of whether you approached from the left or from the right, so from above the number or below the number, in both instances, the function is approaching the same number 3. So what we can say here, and you want to get used to writing limit every time. Somebody asked a question, is there a certain decimal place we should stop when recording the y values? Once you see a good trend, so I would at least get 4 numbers in. This is a good question. I would at least get 4 numbers in. Make sure that you're seeing a good trend. And once you're certain you have a good trend, then that's fine. So, I would feel good after these 2 numbers because I'm like, okay, that really does appear as if it's getting closer and closer to 3. If I went from here to here, this is too big of a gap for me to know exactly what's happening. But from here to here, I can tell that we're zoning in on 3. Does that make sense? No problem. Other questions so far? So when you're doing this notation, sometimes students start to get lazy and they don't put this limit part in. This limit part is not optional. So when I write my answer here, you have to put the limit as x approaches 2, because we are finding the limit as x is going towards 2 of our function, which is x cubed minus 2x squared plus 4x minus 5 is 3. The y values are approaching 3 as x approaches 2. So our real answer here is 3. the full thing is the limit as x approaches 2 of x cubed minus 2x squared plus 4x minus 5 is equal to 3. And once again, oops, this is the left side, right? If you're coming from below the number, you're coming from the left side. And if you're coming from above the number, that's the right side. And we'll get more into that in section 1.3. We'll be talking about it now, but we'll be talking about it a lot more in section 1.3. All right, so fill out the charts below and use them to use them to guess the value of x approaches 0 of f of x if f of x is equal to the absolute value of x over x. All right, let me kind of write it a little bit bigger what we're looking for here. The limit as x approaches 0 of the absolute value of x over x. So I want you to note that in this very first one, if you actually put in f of 2, so if you plug in 2 to that polynomial, right, I'm going to do it on my calculator right now. If you do x cubed minus 2x squared plus 4x minus 5, if you plug it into your calculator, you're actually going to get 3. All right, so if you actually plug this in, the number you get down here is the number you get in your calculator. However, down here, if you plug in 0 to this guy, so if you plug in the absolute value of 0 over 0, your calculator is going to give you a math error. All right, if you type 0 over 0, this is going to give you a math error. There is no actual value when you plug in 0. The only thing we can do here is guess what is happening at that point. So we're going to plug in some values, and we can actually do this by hand. And it's not too bad to do this by hand. So plugging in 0.5, the absolute value of 0.5 over 0.5. Well, the absolute value of 0.5, remember you just make it positive. So 0.5 over 0.5, that's just 1. Plugging in 0.1, the absolute value of 0.1 over 0.1. The absolute value of 0.1 is 0.1, and 0.1 over 0.1 is 1. The absolute value of 0.01 over 0.01. So the absolute value of 0.01 is 0.01 over 0.01. That's 1. So if we're going to make a guess on what's happening, right? All right, it was 1, it was 1, it was 1. Our guess of what should happen is that it should go towards 1, right? And to make it clear, maybe I'll make it clear right here, these are just our guesses, right? We're guessing that it goes to 1. There's no proof of what happens, right? We're just guessing. Same thing over here. So if I do the absolute value of negative 0.5 over negative 0.5, the absolute value of negative 0.5 is positive 0.5. This is just going to give me negative 1. The absolute value of negative 0.1 over negative 0.1 is negative 1. So we get -1 that entire way. Our guess would be that this goes to -1. There's a problem here, right? Because looking at this, on one direction, when we approach 0, it gets closer to 1, and in the other direction, it's getting closer to -1, which doesn't help us. Like, what actually happens at 0? If this one gets closer to 1, and this one gets closer to -1, what's even happening there? These are different numbers. If that happens, then all we can say is that the limit as x approaches 0 of the absolute value of x over x does not exist. All right, DNE stands for does not exist. There is no limit, there is no number that it approaches, because it's different depending on the side that you approach it from. Right, and something to point out, this is a small thing, and I'm not gonna mark people down for it, but it is a pet peeve of mine. We don't say equals DNE. We don't put an equal sign here. It doesn't equal DNE. It just doesn't exist. We say it does not exist, not that it equals DNE. It doesn't equal anything because it doesn't exist in the first place. So an observation, when limits from the left and the right are not equal, that's when they don't, that we say that the limit does not exist, right? So if when you come from the left and when you come from the right, you get different numbers, that means that your limit does not exist. Oops, what did I do? And then we write DNE. So there was a question in the chat box, and I know it got taken back, but I'm still going to read it and answer it because it's a good question. So if it has a negative and a positive, it is DNE. So the answer would be, yeah, so as long as these numbers are different, so if what you get when you approach from either side, if they are different numbers, so if one's negative and one's positive, or one's 2 and one's 3, regardless of the situation, if coming from different sides you get different answers, then it's going to be a DNE. That's a good question. All right, other questions before I move to the next page? All right, so let's talk graphically. So when we're looking at the graph of functions, and I think honestly students tend to get most confused when they look at the graphs, and it doesn't need to be this bad. I promise that it's just kind of it's what it looks like is going to happen. Limits are just what it looks like is going to happen. So we're going to look at some graphs. We're going to graph some stuff ourselves. And we want to think of the limit as the tendency of the y values. So what the y value is getting close to as our x value gets closer to a. So the key to finding limits, deep breath in. Deep breath out. The key to finding limits graphically is to follow along the curve, paying attention to the y values as you get close to x equals a. You want to make sure you get the same value from both sides. This will make more sense when we actually do it, but I'm going to write it down for now. So we are going to graph this function f of x equals the quantity x plus 1 quantity squared minus 1, and we're going to use it to find the limit as x approaches -3 of f of x. If the limit doesn't exist, we write dne. So quickly, this guy right here is a parabola. So kind of a recall from Math 126. This is a parabola. Because there's no negative out front, we know it faces up. It opens up. So it's gonna look like this. Right? This is in vertex form. So vertex form, let me just, I don't know, I guess I'll write it here. Vertex form of a parabola, this belongs down here. I just want to put it up here. Is f of x equals a times x minus h quantity squared plus k, and the vertex is at h comma k. So because there's a minus sign here, the vertex, the x value of the vertex is at the opposite of this value. So there's a vertex at -1. So the -1 comes from right here. H is equal to -1. Maybe I will. This is just a review of parabolas. And then the k value, so the y value of the vertex, is just whatever number you see here. So there's a vertex at -1, -1. So if I'm going to graph this, -1, -1 is right here. Right? I know it opens upward. In order to graph this, you kind of need to plug in values that are close to this x value. So you can make yourself a small little table. So -1 is where the vertex is. So I kind of want to plug in two values that are above -1 and two values that are below -1. So I could do -2, -3, and then I could do 0 and 1. And I'm plugging them in to f of x equals x plus 1 quantity squared minus 1. So if I plug this in, -3 plus 1, here's the mental math I'm doing. I'll erase it after a second. -3 plus 1 quantity squared minus 1. -3 plus 1 is -2, so -2 squared minus 1. That's 4 minus 1, which is 3. right? And I'm doing this each time. So -2 plus 1 quantity squared minus 1, -1 squared minus 1, 1 minus 1, that's 0. So this point right here is the point -3 comma 3. This point, the next point is -2 comma 0. And then the fun thing about parabolas is because, I wonder if I can make it a little thinner. Because they are symmetric about their axis, they're symmetric, you can just flip this guy over here and that's where the next point will be plotted. So if you plug in -1, that's the vertex. So the vertex already has a value, a y value of -1. We already knew that. But 0, these guys right here, because they are an equal distance from the vertex on either side, they're going to have the same y value. So these y values will be the same. And same thing with these guys, because -3 and 1 are the same distance from -1. It's like this point gets flipped over the axis. It has a y value of 3. Oops, I put that too far away though. So if I kind of draw this, I am not an artist. Here's the picture. So I'm going to erase this stuff here because that's just plugging in. All right, I've drawn my picture. Now, we're asking ourselves what the limit as x approaches -3 of this function is. Actually, I'll do this color. So let's see, -3 is right here, right? On this guy right here, we know exactly. Did I get kicked out? Are you guys kicked out or is it just me? Hold on. Start recording again. And let me, there we go. And then I want to view the chat participants. There we go. Cool. All right. So we're looking for this limit. Now we actually know what happens here because we can see the whole picture, right? We know that it actually turns out that this is 3. And if you look, even if I didn't know exactly what happened right here, even if I didn't know exactly what was going on, like if all this was destroyed and there was, you know, just like this mystery area right here, we didn't know anything that happened here, if this was all just disappeared, by the way that this function looks, right? By the way that this looks, we'd be able to see that it probably would end up here. Right? If I wish I had the ability to just do a small bit of whiting out. If I just didn't know this much, if this was all that was missing right here, normally I have like a ruler that I can put down. I would still be able to tell, I would be able to trace my fingers and be like, okay, going this way and going this way, it looks like it should end up right here. So the value of this limit from both directions, right, as we approach from both the right and from the left, right, I'm approaching this way and approaching this way, we approach the same point, we approach the same y value, and that y value is 3. Because regardless of which direction you approach, this x value, right? And we are approaching that x value, right? This x value belongs right here. So we come both directions. We come this way, and then we come, well, this green arrow is kind of off, but we come this way, and we're approaching that same value. We will be doing more, don't worry. Let me scroll down here. I'm just going to go ahead and draw this function. So this is the function that we did on the other page. And I'll show you what this function looks like. So this is the function, the absolute value of x over x. And we want to find the limit as x approaches 0 of this function. And we did this on the other page, but I want you to see what it looks like when you're looking at it this way. All right, so approaching from the right, so 0 is right here, right? This is, I don't know where to put my 0, but it's 0 right here, right? X equals 0 is right here. I'm going to remove it. It's right here. It's at the origin. That's where x is 0. All right, approaching that x value from the left, right, coming this way, it looks like we're approaching -1, right? If I'm just tracing, it looks like we should be at -1 when we get to 0. If I come from, so this is coming from the left. If I come from the right, tracing my finger along here, it looks like we're approaching +1. Now, it doesn't matter that that it's not defined here. Even if this was defined, even if this was filled in, this limit still wouldn't exist. Right? It's all about what it appears to be doing, what you appear to be approaching. And from both sides, you get different answers. So this limit does not exist. So I'm going to go on to this next one where there's an actual graph drawn for us so we can look at this. So we're going to look at this graph and we're going to determine what certain values are. So something I want to point out here, this right here is an open circle. Right? This is an open circle. This is an open circle right here as well. And these are open circles. I'm going to erase this, but those are all open circles. These ones. Just in case you don't have it printed out. Those are all open circles, and then the other things you see are closed circles. I want to point out some things that are going on in this chart down here. Some of these problems are asking for k of a value, right? K of a value is just purely asking for the y value. If it says the limit, then we're looking at what it appears to be, like what we appear to be approaching from both sides. But this says what's the actual value there. So if I'm looking at the actual value, this function is k, right? The actual value of the function, the y value of the function when x equals 2, let me write it down. actual y value, you're looking for the point where it's filled in. So at -2, it's not right here because this is an open circle. The actual value is this guy right here. And that's the actual value of k at -2. So I'm going to make a color guide here. So the actual y value is 3. It actually is 3. K of -2 is 3. That is the y value of the function. Oh, the blue dot was already... Yep. Sorry, I just colored over it. Does that make sense? Yeah, no problem. Let me actually just... I'll do this because that makes more sense so it doesn't look like I'm just like randomly plotting dots. Yeah, no. That's a good question and a good point. I'll do that way. So it's actually at -2, it's actually 3. Where the question is different, oh, and let me make my little color guide, is when we talk about the limit as x approaches -2. So when I talk about this, I wonder if I could, I'm trying to think of how I want to do this because I kind of want to like, oh, we'll just do it this way. We want to pretend like we don't know any of this, and I will erase this in a second. Like we don't know any of this. Right? When you're looking at limits, you're pretending that you've whited out this area and you don't know anything going on here. Now, if you're asked the question, what is the limit as x approaches -2? Okay, well, you're following the function, right? You're following it. And let's look. Okay, well, it looks like it looks like the x value, -2, is right here, right? And as we get closer going this way, it looks like we're approaching 4, the y value 4. And same thing if we approach this way. Either way, it looks like the point should be right here. Right? It looks like the point should be there. So the y value that it looks like it's approaching is 4. Now I am going to undo all of, maybe I should wait till you guys have it written down. But I'm going to undo it so that you can see that what I really am doing. So even though there's an open circle here, what it looks like is happening is that from either direction, the left and the right, that the y value is approaching 4. Does that make sense? So it's like you don't know what's going on in that area, but you can guess. Can I get any questions up to this point? Please feel free to open your mic up to chat. I can't talk. To type in the chat box. Mm-hmm. Mm-hmm. Okay, good question. Yeah. So when it says the actual value, so when you're looking at the first row, you're looking for filled in circles or like actual points on the line. When it says limit, that's when you put your finger on the actual graph and you trace it and you look at where it would be. So the word limit is when you start touching the graph and getting closer to that x value. So you are getting closer and closer to that x value right down here on both sides. And that's where it looks like it's going to be comes from. That's when it's the limit. No problem. Other questions? So then, looking at k of 1/2, what is k of 1/2? Well, 1/2 is like, I don't know, in here, right? Somewhere halfway between 1 and 0. And if I go down, there's an open circle there, right? If you look on the entire graph that we have visible to us, there's no closed circle at 1/2. So k of 1/2 doesn't actually exist because this isn't a filled in circle. The difference between here and here is that that at -2, there was a filled in circle. So we can say that that's the actual value there. But at 1/2, the entire way up and the entire way down, the only place where you even get close is right here, but this is an open circle, so it's not actually even defined there. So it's like this whole space is empty. So there is no value for a k of 1/2. It doesn't exist. However, let's see what color we could use. Let's use pink. However, if I came in here and erased this, and you still knew that 1/2 was where, maybe I'll erase it in a different way. If I erased this part right here, and I'm looking at figuring out what the limit is, so I'm looking at figuring out what does it look like it should be. Well, when I go this way, so I put my finger on the graph and I trace towards 1/2. So 1/2's right here. So I trace towards 1/2. It looks like it should be at -1. And then same thing coming from the other direction, I trace along the graph and it looks like the y value should be -1. So from either direction, even though I don't see anything on the graph, even though I had it empty there, from either direction, it looks like the y value should be -1, which makes this limit -1. So I'm going to erase it so that it is back here. So coming this way and coming this way, that limit is -1. And this limit exists because both sides approach the same number. Now, this one's not on this list, but I'm going to ask you, what is k of 2? K of 2 is not on this list, but if I ask you, what is k of 2? I'll take answers, either microphone or chat box, I don't care. What is k of 2? Seeing some answers, seeing some zeros. Excellent. Excellent. Yeah, so k of 2 is 0, right? If I look where the filled in point is, so here's 2, where the filled in point is right here, that's the y value 0. K of 2 is 0. However, right, if I white out this area, right, and all I tell you is that 2 is right here, right? If I white out this area and I trace from the left, so from the left I approach and I'm like, well, it kind of looks like it should be at 0, right? Like it looks like if I come from the left it looks like that y value should be 0. But then I come this way and I come from the right and I'm like, I don't know, it looks like it should be, I don't know, maybe 2. It looks like the point should be right there, right? If I widened it out, this part, like from the right, it looks like the y value should be right here at 2. And then from the other direction, it looks like it should be here at 0. So those numbers don't align, right? If I look back here, right, when I can't see anything, what in the world is happening here? I don't know. It doesn't look like it can, like, if it connects, it's going to connect in a weird way, right? You can't really tell what's going on as you're really close to it. So once again, from this direction, it looks like you're approaching 2. From the other direction, it looks like you're approaching 0. Because they approach different y values, the limit does not exist. Does that make sense? Does that one make sense for everybody? Even though k of 2 is equal to 0, the limit as k approaches 2 does not exist. Then looking at, I guess I shouldn't have done this yet. What color should I use? I don't like brown. I don't know, let's use like a fun green. Oh, but we've already used green. I don't know, like maybe a fun red, like a burnt red. All right, so looking at k of 3. K of 3 is the value of the function at 3. So here's 3 right here. And there is a filled in circle right here. So that's the actual value at x equals 3. The actual y value right over here at x equals 3 is 5. Now, looking at the limit, right, I'm going to, once again, erase here. And let's do, oh, we haven't like done like an orange. Let's do an orange. So now, if I'm drawing, so I'm doing a limit now, so that's not very orangey. If I'm drawing along the function, because I'm doing a limit, I'm drawing along the function, it looks like the y value it's approaching is 5 from the left. If I come along, sorry, I should have done that from the other direction. If I come along from the other direction, from the right, it also looks like the y value should be 5. So in both directions, it looks like the y value should be 5. So the limit would be 5. So in some cases, the function is defined there, but the limit is different than the actual y value. So in this case, the y value was 3, but the limit as x approached -2 was 4. So sometimes that happens. Sometimes down here, the function itself doesn't exist, but the limit does. Sometimes the function exists, and once again, the function exists there, right? It exists at 2, but the limit doesn't exist because it's broken up. And then sometimes everything is the way it should be, and the value of the limit is the same as the value of the function. So there's a bunch of different things that can happen with these limits. Can I answer any questions on that so far? Okay, I'm going to scroll down here. So basically everything I said is said right here. In example 1.5, it showcases the reason that except possibly at x equals a is included in the definition of a limit. So like even though the limit as x approaches -2, not -2, even though the limit as x approaches 1/2 of k of x exists, so right here, this limit exists, k of 1/2 itself does not exist. So basically what I said up there. And then the other time where we see that happening is at 2, when x is equal to 2. So we see at x equals 2, or not 2, -2 is what I mean there. At -2, this is a situation, it's a little bit different, but like it exists, but the limit is different than the actual value. So k of -2 was 3, but the limit as k approaches negative, or not k, as x approaches -2 of k of x is 4, and those are different numbers. So we're going to do the same thing down here with this graph. I want to point out that there are holes right here. This is a open circle, this is an open circle, and this is an open circle. I know it's kind of small, but the dots, those are closed. This is the function p. So p of -2, what is p of -2? Looking at this graph, go ahead and in the chat box, what is p of -2? Remember, this one's not the limit, this is the actual value of the function. I'm seeing some threes. And I see some threes. All right, excellent. Yeah. So looking at this function at -2, which is down here, if you look, there's a closed and an open circle. The closed circle is the actual value there. So p of -2 is 3. However, the limit as x approaches -2, right? If I erase everything here, if you approach from the left, it looks like you're approaching the y value -1, and if you approach from the right, it looks like you're approaching the same place, right? If I take this away, it looks from both directions like you're approaching -1. This is -1 right here. So because for the limit, from either side, when you approach -2, it looks like it's approaching the same number, and that number is -1. The limit as x approaches -2 of p of x is -1. Go ahead and try and fill the rest of these out. I'm going to give you a minute to just fill out these guys here, right? And then I will go through and we'll talk about the answer. So just take a moment to fill those ones out on your paper, or to, if you don't have it printed off, to just look through it. You don't have to necessarily type it into the chat box. Just look at it and figure them out. All right, so for P of 2, what are we getting for P of 2? I'm seeing some ones. Excellent, excellent, beautiful. Yep, so that's the actual value, the actual y value, which is 1. And what about the limit? The limit as x approaches 2 of P of x. Beautiful. Seeing some DNEs in there. Yeah, so for this guy, if we approach from the right, or sorry, from the left. So here's the thing you're going to learn about me really fast. I mix up on my lefts and my rights a lot. I don't know why. I'm a grown adult. It just happens. So you'll have to excuse me when I inevitably do that a million times this semester. So if you approach from the left, you are approaching 1. If you approach from the right, you're approaching -2. So this guy does not exist. And let's do this color. What about the limit as x approaches 4 of P of x? Limit as x approaches 4. Beautiful. Seeing some answers in there, seeing some -2s. Excellent. So, yeah, approaching, so -2 is right here. No, sorry, that's not what I meant to do. 4 is right here. And if you look coming this way, coming from the left, it looks like we're approaching -2. And then coming from the right, it appears like we're approaching -2. So from either direction, it looks like we're approaching the y value -2. So that's the value. That's the value of the limit. All right. What about the limit as x approaches -1? The limit as x approaches -1 of P of x. I'm seeing some 2s. Yep. So approaching, here's -1 right here. Right. Approaching -1 from the left, it looks like we're approaching the y value 2. Approaching it from the right, it looks like we're approaching the y value 2. So the limit as x approaches -1 of P of x is 2. Mm-hmm. This one? Mm-hmm. So you would be looking at, so when you have the whole graph, what you're looking at, so you can see that it actually, hits here. So you could draw your own dot in because you can, oh, it hits right here. So you can draw your own dot in there. And then you can see that like it approaches this way and then it approaches this way. And that it, because there's no hole in the graph, because it's one solid line, anywhere that there's a solid line, you can draw solid dots on because those are all defined parts of the function. So we can just draw a dot on there and then you can see that it approaches this way and it's filled in right there. So you could say that that value is -2. Does that make sense? Yeah, no problem. There you go. There we go. Other questions so far? All right. So there's some shortcomings of methods of guessing. All right. For example, if you're looking at this limit right here, right? If you plug in these values, so in your calculator, if you plug if your calculator's in radian mode, the values to this function. So if you do sine, we're trying to get closer to 0, right? So if you do sine of pi over 0.01, right? Sine of pi over 0.01, I get 0. And you try getting closer to 0, you get 0.001. Right? You do that, you get 0. Right? If you try doing sine of pi over 0.0001, you'll get 0. Right? Which would make you think that coming from the right, coming from the above part, that you're going to go to 0. And if you try the negatives, if you try sine of pi over negative 0.01, you're also going to get 0. If you go this direction, you're also going to get 0. So it would really appear like the limit should be 0. Right? You're going to get 0 every time if these are the numbers you choose. All right. So this would make us think that that limit is 0. However, if you choose other small numbers, so if instead, like maybe you made this 1 into a 2, maybe not a 2. I guess you're going to have to use fraction. Okay, try like a 3. If you use like a 0.003, you're going to get different numbers. And here's what's happening. So if you try these numbers, these are getting increasingly smaller. If you try these numbers, you're going to get -1 as an answer. But here's what's really happening. This. All right. This function gets closer to 0 and then just wiggles. It just wiggles erratically. Right? It won't stop wiggling in here. It wiggles infinitely. There is no limit because you can't even tell what's going on in here because it just wiggle, 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 wiggle. This limit doesn't exist. So this isn't the best method in the world. Now, of course, none of the problems I assign you are going to be that I ask you to do the numerical guessing method. None of those methods are going to have a problem like this. We have other methods that we're going to talk about. These are kind of like the numerical guessing method is the least used method that we'll use, but it is a method and it's a way of talking about limits. But it has its shortcomings, and one of them is this particular function where it just gets wiggly and it can appear depending on the numbers that you choose, it can appear that it approaches one thing when it actually approaches nothing at all. So that is one of the shortcomings of that method. Can I answer any questions? So that ends 1.1, and we're supposed to get through 1.2, but we'll just start 1.2 and we'll finish it on Wednesday. But can I answer any questions on 1.1 before we move forward to 1.2? All right. So really what we're going to spend a lot of time doing is calculating limits algebraically, using algebra. The thing I told you was most important, more important than anything else, algebra. So there are some properties that limits have. Something you need to know as I go through these is that the letter C and the letter K are both going to represent constants. That is numbers, just numbers that don't change. Those are constants, just numbers. So we're going to suppose for all of these rules that the limits exist for f and g, because we're going to talk about functions f and g, and that the limit as x approaches a for both of them exists. That has to be true for these rules to work. So the constant rule. The constant rule is that the limit as x approaches a of a constant is just the constant. So as an example, the limit, it's a weird limit. The limit as x approaches 7 of 54, which is a constant, is just 54. So if on the inside of your limit there's just a number, that limit is just that number. It doesn't matter what this is approaching. This could be approaching anything. It doesn't matter. There's no x in here, so it doesn't matter. You're not plugging x into anything. This is 54 all the time. That's the constant rule. The constant multiple rule, and maybe what I'll tell you right now, you do not need to memorize, you don't need to memorize the names of these rules. You need to memorize that these rules exist and what they do, but you do not need to be able to say, this is the constant rule. This is the constant multiple rule. That's not a thing I care about. Just thought I'd point that out. All right, so the limit as x approaches a of, so a constant k times a function. This is the same thing as if you took the constant outside and left the function and just took the limit of the function. I'll give you an example. And maybe I'll also draw what's happening here. This k can move to the outside is what's happening. An example of this. If you have the limit as x approaches 2 of 4x squared, this 4 can come out front. So this is the same thing as 4 times the limit as x approaches 2 of x squared. And these will make a lot more sense when we get to finally using them. The sum and difference rule. If you have the limit as x approaches a of f of x plus or minus, it doesn't matter which, g of x. With this, you can take this limit part and give it to both of them instead. It's almost like what we'd hope would happen. So this would be the same thing as the limit as x approaches a of f of x, plus or minus, depending on what you're working on, the limit as x approaches a of g of x. As an example, let's say we have the limit as x approaches 0 of x cubed minus 2x. I can take this limit, give it to both of them, and I'd get the limit as x approaches 0 of x cubed minus the limit as x approaches 0 of 2x. So there was a minus sign, which is why there's a minus sign here. And I just gave the limit to both of these terms in here. For the product rule, you can kind of see where this is going. If you have two functions where they are being multiplied together in the inside of a limit, you can take the limit and give it to both of them and just take the product of them, of their limits. So you can do the limit as x approaches a of f of x times the limit as x approaches a of g of x. As an example, we have the limit as x approaches pi of x sine x. So this is x multiplied by sine x. So we can give this limit to the x and the sine x. And this would be the limit as x approaches pi of x times the limit as x approaches pi of sine x. You can kind of see where this pattern is going. So if you have the limit as x approaches a, and we have a quotient of two functions, f of x and g of x, you can give that limit to the top and to the bottom. You can just put it on the top and bottom instead of having it on the outside. So you'd have the limit as x approaches a of f of x over the limit as x approaches a of g of x. This works as long as the limit as x approaches a of g of x is not 0. If it's 0, then you have a problem, right? That doesn't work. But as long as it's not 0, this will work. So as an example, if you have the limit as x approaches 2 of x plus 1 over x squared, this is the same thing as the limit as x approaches 2 of x plus 1 over the limit as x approaches 2 of x squared. The weird one is this composition rule. So the composition rule says that if you have a composition of functions, so for instance, you have f composed with g of x. So this is g of x on the inside of f of x, it says, hey, you can go ahead and take this limit part and move it to the inside so that you would have f of the limit as x approaches a of g of x, provided that f is continuous at the limit as x approaches a of g of x. Now, many of the functions we're going to talk about are continuous on their domain. So don't think too hard about this contingency. It is a contingency, but it rarely is a problem, so don't worry too much about this. It's basically saying as long as the outside function is a continuous function, you can do this. So for instance, sine is a function that is continuous on its domain. So now there's issues of if this is approaching 0. It's not an issue for the most part. What I'm trying to say is don't worry too much about this. Most of the time you can just move the limit to the inside. It's not a big deal. So for instance, on this guy right down here, because sine is continuous on its domain, and in particular at 1/5, it'll definitely be continuous. You can move in the limit and you get sine of the limit as x approaches 5 of 1 over x. Same thing here. You can move this to the inside of the square root function. So you have the square root of the limit as t approaches 9 of t squared plus 10. So you can move that limit to the inside. Some quick notes. X is what we call a dummy variable. So in all of these ones, all the examples I showed you, there were x's. Well, this one has a t. All the ones I use up here, we used x's, right? X, 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 x. X is a dummy variable. You should be paying attention which variable is being used down here. So for example, in this guy here, it says the limit as t approaches 5 of x squared. Because this is talking about t and not about x squared is a constant. So the only number that's changing is the variable that you see right here. If this variable is different than this variable, then the x isn't changing. It's just the t that's changing. So x is treated as a constant. And if we look at the constant rule, the limit of a constant is the constant. So it doesn't matter what t approaches, x squared is going to stay x squared because x squared doesn't rely on what happens to t. This second one is just saying what I told you before. In practice, we can pull the limit on the inside as long as no funky stuff happens. So in general, you can pull the limit on the inside. There's rare cases where you can't, but you'll notice because there's funky stuff happening. All these rules can and will, let me squiggly under that, and will be combined together. So you need to get comfortable with all of them. Very rarely are you going to be using just one of these rules at a time. You're going to be using them together. Right? An important implication of rules D and F, or point of D and F, is if you have the limit as x approaches a of a function, and then this is raised to a constant up here, so r is a constant, this means you could bring that limit on the inside and then just raise the entire limit. To that number. So let's move to the next page And let me label some stuff here. All right, this is going to be for f of x. We have 3 functions we're going to be talking about on this page. All right, this is for f of x. There's a second function, g of x. Remember, these are all different functions, and we're going to be using them. And this is the function h of x. I know it's kind of tiny and blurry, but we have 3 different functions we're talking about here. So if I look at this first problem, it says the limit as x approaches 0 of f of x minus 2g of x plus 7h of x. I'm going to split this up into something that I can use. So the first thing I can do, I know that because it's addition and subtraction that I can split up the limit by distributing it over everything. So this is the same thing as the, oh, I don't want red, as the limit as x approaches 0 of f of x minus the limit as x approaches 0 of 2g of x plus the limit as x approaches 0 of 7h of x. From here, I know I can pull the constants to the outside. So this is the limit as x approaches 0 of f of x minus 7 times the limit as x approaches 0 of g of x. Oops, not 7. That one was supposed to be a 2. 2 of g of x plus 7 times the limit as x approaches 0 of h of x. And now we can figure out, I should have used a different color for h of x. Oh well. They can figure out each of these. So for instance, the limit as x approaches 0 of f of x, we have that right here. That's -1. The limit as x approaches 0 of g of x, we have that right here. This part is 0. The limit as x approaches 0 of h of x, so we have to look at this graph, right? So as we approach 0, from either side, it looks like the limit as x approaches 0 of h of x is 1. So if I make some replacements, the limit as x, no, sorry, that's not what I meant to write. If I make replacements, I get -1 minus 2 times 0. And the limit goes away, right? Because we're replacing the entire thing. We know what the limit is. We're replacing it. Plus 7 times 1. So -1 minus 2 times 0 is 0. 7 times 1 is 7. So -1 minus 0 plus 7, that's going to be 6. So the answer to that problem is 6. So for this next one, we're going to be doing that same process. So I'm going to kind of do a few things at once. The first thing we could do, right, is because this limit is for a quotient, we could move that limit to the top and to the bottom, right? We could make it so it's on the top and bottom. And then from there, we can distribute it to each of these pieces. I'm going to use black this time so I can color code better. So on top, we'd have the limit as x approaches -2 of g of x squared plus the limit as x approaches -2 of 2 times f of x minus the limit as x approaches -2 of the square root of h of x all over the limit as x approaches -2 of f of x cubed plus the limit as x approaches -2 of 1/3 g of x, times h of x. So really, I thought there was a plus there. It's just getting distributed once there, and we will distribute it more. So there's a few things that are going to happen here. So first up, I've distributed it. Right now, I'm going to move it inside where I can. So this limit can move onto the inside right in front of the g of x. This 2 can move to the outside. This limit can move to the inside. This limit can move to the inside. This limit can get distributed once to this part and once to this part. And I know we're out of time here. I am just going to finish up this problem. If you have to leave early, that's fine, but I'm going to finish up this problem. So moving things around, like I said, we have the limit of x approaches -2 of g of x, and then the whole thing will be squared, plus 2 times the limit as x approaches -2 of f of x, minus the limit as x approaches -2, the square root rather, because we're moving it on the inside, the square root of the limit, down here, we're moving the limit onto the inside and then cubing it. And then we're distributing the limit as x approaches -2 of 1/3 g of x times the limit as x approaches -2 of h of x. Now, technically there's one more step, but I'm going to like erase it so that it looks like we did it all in one. This 1/3 can come to the outside. It's a bad arrow. This 1/3 can come to the outside here because there's a 1/3 in front. So what I'm going to do is show you it there and then redo it this way. So plus 1/3 limit as x approaches -2 of g of x. Coming up here, looking for our -2 ones. So the limit as x approaches -2 of f of x is -2. I'm going to write it down here. The limit as x approaches -2 of f of x is equal to -2. For g of x, it's 3. And then approaching -2. So approaching -2 from the left and from the right, both ways it appears to approach 4. So I'm going to replace everything with what it should be. So for instance, the g of x right here, this limit should be 3. This guy right here should be -2. On the inside here, this should be 4. This guy right here is -2. This is 3, right? And I'm just pulling it right from over here. And this is 4. So with my replacements, I have 3 squared plus 2 times -2 minus the square root of 4 all over -2 cubed plus 1/3 times 3 times 4. Right? All that comes from using this information and just simply plugging it in here. So I moved all the limits around until I had it in a form where I could exactly find those limits. And then it's just plug and chug. So we have 9 minus 4 minus 2, just simplifying. -8 plus 1/3 times 3 times 4 is going to be 4. So on top we have 3, and on the bottom we have -4. Hold on, I'm wondering right here. Okay. Because I have a different answer written down but that should be right. So -3/4 should be right. I have a different answer written down in my own notes, but I'm seeing some math that I did wrong in my own notes, so. There it is. So a lot of work. It gets to the point where you can do it very quickly because you'll go from just this step here, the original, just down to here, and then you can get your answer pretty quickly. Anyway, so the homework has been posted. Some of it you'll be able to do, some of you won't be able to do yet, but definitely after Wednesday's lecture you'll be able to do. I hope you have a fantastic Monday. If you have questions, send me an email. Other than that, you are free to go. Have a fantastic Monday. We'll go ahead and stop this recording.